the simple mechanism that, for instance, you can do in this case to see where the data is dropped is to ask for acknowledgement at every hop, like in this picture, which is quite a long, the overhead is quite big because it's linearly with the size of the path. So because we know the path, we can do much better than that. You can actually do an adaptive probing in which you you look at the path like an interval and you keep breaking it in half to detect where it happens. Now, it's not, or things that you have to take into account is the following. First of all, your adversary can move. So how do you start this? You have to keep in mind that an adversary can move from one point to another. So at the worst case, you keep all the probings going on because you may have actually more links that are problematic. That's one aspect. The other aspect that I would like to mention is that once you have such a mechanism in place, well, guess what? He can be attacked too. If the attacker detects, he knows that this particular message that goes over the network is a probe, it will treat it differently. He will let the probe go, but he will drop all the data. So because of that, you have to have, once we have such a mechanism, we introduce it in the protocol in a way in which we are able to mask that these probes or the acknowledgements, they look like different packets. And there are different ways in which you can do that. And cryptography helps you a lot there. So this is one of the things that I wanted to mention to you. The link management, as I said, basically what we do to give you the details. Basically, what we do, we use a mechanism that is very similar with the way TCP also handles congestion. Every time we detect that there is some loss, we double the link. We double the weight of the link. So this is the multiplicative aspect. Now, if we see that after some time nothing bad happened on that particular link, in order to rehabilitate the link, we decrease it then by 1. So such that over a certain amount of time, our analysis shows exactly how much damage you can bound. How can you bound the amount of damage that an attacker can create? Now, I promise you that I'm going to show you some simulations, and I want to use the time to do it now. So what did we simulate? Well, first of all, so this is not a real implementation. We used the NS2 simulator. We implemented this protocol, and we performed simulations using 50 nodes that were just regular nodes in the network. And then what we played with the number of adversaries that can be introduced in the network, with the types of attacks that they can perform, and where they are positioned. Because it turns out that it's very important where the attackers are positioned and the combination of the attacks that they can create. Basically, we wanted to say, from the adversary point of view, what is the maximum damage where should I be positioned and what attacks should I do such that I can create the maximum damage? Which means maybe I don't need to compromise too many nodes. Maybe all I need is one node and I will create a lot of damage. So these are details about the way we perform the simulations, but the things that are important are how many nodes are correct, which is 50, and up to 10 can be adversary. So the configurations that we looked at are the following. The most simplest one, so we also want to play with wormholes. So we will also need at some point configurations in which we have 2 nodes. So the configurations that we looked at, one of them is called central wormhole. In other words, in the area in which we are performing the simulations, we put a wormhole that is centrally placed, which means the adversary compromises these 2 nodes, control these 2 nodes, and can perform any type of attack. Then we looked at 2 other more configurations, 2 wormholes placed like that, and the strongest one, which is the last one, you have 5 nodes, and you can have wormholes between each of them, which means that in the last case, what you actually have, and that's so strong, is because you have a network within the network, and the network within the network is controlled by the adversary. And the Cross of Death name is not my creation. I also thought it was funny, but actually Herb came up with the name. He's good with names. So the first thing that we wanted to look at is what is the damage that an attacker can create if he can perform more sophisticated attacks? Is it important or not that an attacker can control more paths or not? The Blackhole, so in this picture what we did, we took AODV, which is a well-known routing protocol for ad hoc wireless networks. We took our protocol, and then what we did, we played with, for different speeds, what we said, let's look what happens when I take the black hole attack, which means dropping data, and also adding to this the ability that the attacker can perform flood rushing, which means he can control more paths. On the X, we have how many adversaries are in the network. So the ones that are below, you can see how much data actually it's dropped. This is the delivery ratio. So the higher you are, the better, which means that you don't lose a lot of traffic. The lower you are is not good. This means that most of all that traffic, how much you dropped is the data, how much the graph goes down, it's the data that you dropped. Not a very good idea, so not a very good thing. So in this case, for example, you can see that if I look at the worst case, which is 10 adversary, I think it's about 50 or 40% of the data makes it. So it's half of it makes it, half of it doesn't make it. But all that is happening here, as I said, is just performing this flood rushing attack. There is no tunneling going on. Now, if I take that wormhole central configuration that I told you about, this is what's going on. Again, in all the graphs, you're going to see AODV and our protocol. Now, for this case, what happens if you have only a wormhole attack, or if I combine the wormhole with the rushing? Is there any impact or not? Maybe there is no impact. Of course, we look from the perspective of adversary because we want to know how can we defend. So we want to see what's the best. So as it can be seen, look for the last, what's the color? Magenta or lila, or I don't know the color. The last one, you can see that when you start combining, when the attacker starts combining the attacks, he can create a lot of damage. And in this case, there are only two adversaries, only 2 nodes are compromised. So you have a network of 50 nodes in which 2 nodes manage to drop the data delivery to 40%. Let me see okay. The other thing that we wanted to look at is its position, where the attackers are positioned. Is it important or not? From the attacker perspective, if the position is important, he will go for some particular nodes. Otherwise, it's just randomly compromised nodes. So as it turns out, actually, where the position is extremely important, because depending on where the attackers are positioned, they can create much more damage. And also what we try to do, so we look at position. The other thing that we look at, coordination between the attackers. And I think that this is what I had here, yes. So is it important that you have that the attackers coordinate or not? When the nodes are randomly placed, there is no coordination between the attackers. If the attackers can coordinate, actually they can create more damage. And this is what we were showing with looking at the cross of death configuration. It is worth mentioning. I mean, I don't want to say that this protocol is the best in the greatest of the greatest. It's just the first try of looking at, can you do anything about dropping data? So, for example, ODSBR doesn't react very well if you have many links, many adversary links in the network. And this is what the complete coverage configuration shows. The more compromised links are in the network, the slower the protocol reacts. Yes, it will find them in the end, but it takes a long time. So it depends on the nature of the application. Maybe the price is not acceptable. So this is what we were trying to show by looking at this particular, why we chose this particular configuration. Well, because the transmission range, the way that we chose this configuration such that given the area that we have and the transmission range of each individual node, this network here basically covers all the communication that goes in this area. That's why we call it complete coverage, because basically you cover everything. You missed, I think, that a little bit from the corners of the square, but other than that, the attackers really can overhear all the communication, can reach the point. So this is, again, we are looking at what's random placement with number of adversary versus having the complete coverage. So to give you like a small summary, based on the simulations that we did, there were 2 things that we conclude that were very problematic from the point of view of designing the protocol and very, very good for the attacker. And one of them was flood rushing. Actually, in most of the cases, that was the attack that